let's do some lyrics. Come writers and critics who prophesize with your pen and keep your eyes wide, the chance won't come again, and don't speak too soon, for the wheel's still in spin. After pressing the Run button, you see the lyrics floating onto the screen. The web app you see here is called CLJ Tiles. It is open source and hosted on GitHub pages. You can see the address here. While some more lyrics is quoted, maybe you open the web page and come along. Change to page 10. And there's no telling who that it's naming, for the loser now will be later to win, for the times they are a changin'. Make sure to connect the last line. Press Run and see the lyrics. Go to page 11. For the wheels still in spin, for the times they are a changin'. Now watch the text rotate. CLJ Tiles is a collection of tutorials in the form of puzzles. And yes, they are all Clojure tutorials. The app uses Blockly, which is a library for graphical programming. No software is needed to play with the puzzles. That is, other than a web browser. No active web server is needed. It's all Clojure script hosted on GitHub pages. CLJ Tiles is a single-page web application. There are several sections, all containing a handful of puzzles. All in all, there are 13 sections and 137 puzzles. A large part of it is devoted to physics. The culmination of all this is the modeling of the driven pendulum. Go to the section called Pendulum Result. You see all kinds of rather complicated stuff. Coordinate transformations, Lagrangian functions, potential energy, kinetic energy. You do not have to understand all this. This video will carefully explain the basics. In such a way, it will not get as far as to explain all this. But press Run to see a nice equation. Now go to section 2. Calculate the average of 20 and 40. Drag 20 in front of 40 and divide by 2. Press Run. The result is of course 30. The code which is generated to get this result is shown on the right-hand side. Here you see the first thing which might be surprising. The code which is executed is Clojure code. That means you have prefix notation. The plus sign is in front of 20 and 40. If you look at the blocks, you see infix notation. The plus is between 20 and 40. This is a design decision of CLJ Tiles. The idea is to make Lisp more palatable. One reason why people do not like Lisp languages is parentheses, especially in the wrong places. There are no parentheses in the blocks, so this obstacle on the way to Lisp is removed in graphical programming. The second big reason why people find Lisp awkward is the prefix notation in mathematical formulas. This is the reason why CLJ Tiles has infix notation. The hope is to make onboarding easier this way. As you will see, the later puzzles are physics tutorials. They are examples taken from the book Structure and Interpretation of Classical Mechanics, SICM in short. Those physics puzzles try to show to physicists the advantages of functional programming. And physicists are used to read infix notation. Of course, they quickly learn and accept the prefix notation, but there needs to be a bridge. This is provided here. Infix notation is only implemented for simple expressions. Open the parser by right-clicking on the workspace and type +1, 2. Press Insert. You see the parser converts this to infix notation. Press Run. The code generated is proper Clojure code in prefix notation. But by the time people work with the parser and analyze the generated code, they'll get it. It is important to say that the code displayed is for informational purposes only. It might be handy for pasting it into a text editor to start developing your own programs. Open the parser again. Type +1, 2, 3. Insert, and there you have prefix. Only simple expressions are treated in a special way. Step back to page 24 and again to 25. The puzzle is reset. You can also calculate 20 divided by 2 plus 40. It is equally well. The solution of the puzzle is not checked by CLJ tiles. Almost no puzzle is. But there are a few exceptions. They act as a proof of concept for fancy output. If you go back to page 7 and run, you have the standard output. Result on the left-hand side and the code which was executed on the right-hand side. Now complete the puzzle. You see that in this case, the correct solution leads to a non-standard output. Here, CLJ tiles explicitly checks for the result and jumps to a special routine for the output. Again, in later examples, this is nowhere the case. Now go back to section 2, page 26. Complete the puzzle and press Run. A variable called the average is defined and printed. Accordingly, in the lower section, you see the printed value, which is 30. The result of the program itself is nil, because println does not return anything. Reset page 26 and run. You get an error message. It is actually not called error message, but code interpretation result. Sometimes a workspace is not yet meant to run. You did not make a coding error, you just ran early. So the name error is simply wrong in the case of puzzle solving. Right-click on the number 2 and inspect. You now see 3 reasons why no end result is shown. The first reason being the variable the average dangling on top. The second is for the ill-formed def. The third again for dangling the average. There is more than one reason displayed because inspect tries to run every expression separately. This is different from the run button, which simply runs the program. Move the number 2 out of its block and inspect. All of a sudden you get a result. Clojure was able to evaluate the expression despite all the other unsolved issues. The value 2 is printed together with its type, which is number. Types are very helpful. You will see this later on when you try to understand the modeling of physical theories. The display of types is possible because, within CLJ tiles, parts of SICM are spec'd via Clojure spec. Go to 27, complete and run. The function sayWelcome is called with the value Clojure, and the text Welcome to Clojure is printed. To understand better what is going on, inspect the parameter called what. Indeed, it carries the value Clojure and is of type text. Now go to page 28. It is the same puzzle as before, but split it up a bit more. This means it is more difficult. You can see that the blocks have different colors depending on the number of slots. Blocks with 1 slot are violet, 2 slots is green, 3 slots is blue. The blocks are all constructed in the same way. They start with a name, like defen, println, sayWelcome, and have 1 or more slots. The defen is not special in any way. It is just displayed vertically, but this can be changed for any block. Right-click on defen and select Inline Inputs to see this. In the same way, you can have external inputs for the print line block. But that does not make sense from a code formatting point of view. So revert this. Because the syntax of Clojure is so sparse, it leads itself perfectly to an implementation in graphical blocks. Now solve the puzzle. Connect the variable name what as a parameter. Connect the print line to the function body. Complete the print line statement with the text welcome to. Finally, call the function. Press run to see whether everything is correct. Sometimes the colors play out nicely and separate the different blocks in a clear manner. This is here the case. But sometimes it does not play out as well. When you go forward one page, it is green all over. What helps a little is the slight upward shift in nested blocks. Up to now, you solved 4 puzzles from the part of CLJ tiles which covers the Clojure basics. They are covered in sections 1 to 4. The examples are taken out of the book Getting Clojure by Russ Olsen. Section 5 is devoted to simple web programming with reagent. It will be skipped here. As a short glimpse, go to the section called Rocket and Run. Launch the rocket. The example is adapted from the book How to Design Programs. If you drop down the Sections menu, you see that Rocket is followed by higher order. But go to Lagrangian at first. In what follows, maybe you are not understanding immediately what exactly is going on. The hope is that you stick longer to this video when you do something while watching. So try to code along and keep moving the blocks. You learn by imitation as you solve puzzles. One important note. CLJ Tiles is not meant for developing programs. For that, a text editor is still best. The puzzles in the section Lagrangian are based on the SICM book and utilities. Originally, the SICM utils are written in MIT Scheme. In the last years, the SICM utils have been ported to Clojure by Colin Smith. Sam Ritchie enhanced and ported them to ClojureScript. This is the port used by CLJ Tiles. It is the reason you can follow along in the browser. As you can see, this page has an explanation that should help solving the puzzle. It reads, a mathematical vector is created with the function up. The notion mathematical vector is a bit clunky, but it is used to make clear that this is not a usual Clojure vector. A mathematical vector is a distinct kind of object. The vector you create here is also called up vector or column vector by mathematicians. From now on, the word vector is meant to be in this sense. By looking at the vectors in the explanation, you might guess how to solve the puzzle. The number 1 goes to the left. Sine of pi is 0 and goes to the upper right, leaving only one place for the square root of 4. Press run. The result is up 1, 5, 9. You can clear the output to get back to the explanation and see that you solved correctly. You learned that 2 vectors can be summed by simply using the plus sign. In standard Clojure, that is not possible. In CLJ Tiles, the plus operator is replaced by SICM utils to make this happen. Inspect the whole green block. First of all, the vector is now nicely formatted. And second, you get all the type information for the result. You see that the result is a column vector which consists of 3 numbers. You can also inspect the blue blocks. Start with the left one. Again a column vector with 3 numbers. Inspect the right blue block. Here we get a new type, an expression. If you inspect pi, you get a hint why this is. Pi is a symbol. Apparently, when the function sign is fed with a symbol, it returns an expression. Sometimes the function sign returns a number. You can probably guess yourself when this is. In any case, you can always try out. So we already have 4 different kinds of mathematical objects in this simple example. There are numbers and symbols, which we already know from standard Clojure. In addition, you have a type column vector and a type expression. They are provided by the SICM library. All of those mathematical objects can be used in calculations. In other words, you have a computer algebra system in the browser. Now fill the upper left slot with the green block. Press Run. The result is printed nicely formatted as before, this time without the types. Again, all this formatting is provided by the SICM utility. It is just consumed here as a low-hanging fruit. Switch to the next page. You can complete it just by pulling all pink blocks to the left. You have created a function which takes time as a parameter and returns a vector. Inspect the function call. The result is a vector of numbers. For example, the first number is 4 times 10 plus 7, which equals 47. Inspect the parameter time in the function body. You see that the vector is indeed generated at time point 10. Now go to page 88. Drag the symbol t onto the slot. Inspect the parameter time in the function body. It is the symbol t because that is the symbol the function has been called with. Inspect the first green block in the function body. It is the expression 4t plus 7. You just perform the multiplication with the symbol. Clear the output and run. Here you see what physicists call a time-dependent vector. Now go to page 83. Look at the violet block. This block is of the usual form you already know. It has a name in its first place and 1 slot. The slot is filled with the string 3 equals. Now inspect the block. The result of this block is a function with exactly 1 parameter. For comparison, go to page 85 and look at the square of 2. This is the same kind of violet block. It has as well only 1 slot. Inspect it. The result is a number, the number 4. You have seen that before. Now back to page 83. Evaluate the violet block again to remember that this block returns an unnamed function. You want to find out what this unnamed function does. You might guess that the beige-colored block has something to do with this. It looks different from the others. It just consists of 2 slots. Try it out and fill the first slot. Press Run. The result is the text 3 equals 3. So the string 3 equals within the violet block is concatenated to the number 3. Whenever you see this beige-colored block, you know that you have to think twice what is going on. You are dealing with a concept that is at the heart of functional physics. When in doubt what is going on, you can always inspect all involved blocks and make sure to understand whether they return a function or something else. It helps to know that beige-colored blocks always have exactly 2 slots. There is no other kind. Go to page 95. Complete the upper half of the puzzle. Drag square D into the first slot and sign into the second slot. Inspect the whole block. It is a function, but you cannot see how it looks like. You need to apply it to some argument. So finish the puzzle and press Run. The result is minus sign. You just calculated the second derivative of the function sine. It is very common that beige-colored blocks are nested, like in this example here. It is all the same color, which makes nesting hard to spot. This is the reason for the closed paren in the middle of each block. It acts as a visual guide. With a bit of patience, it is easy to spot that the nesting is one fold here. Again, it helps to remember that beige blocks always have exactly 2 slots. Now, take another look at the result. It is interesting to know its type. One might guess it is a function. The derivative of a function always is a function, after all. That is perfectly true, but there is a catch. First, inspect the pink sine block. A function. Then inspect the whole block. It is not a function, it is an expression. Inspect the inner block. A function. This is the real second derivative of sine, an unnamed function. Especially, this unnamed function knows nothing about a symbol or variable named t. To sum up, if you want to know how some function looks like, you need to apply it to some argument. But you pay a price for this curiosity. You turn a function into an expression. And you cannot take the derivative of an expression. That is what functional physics means. You take the derivative not of expressions, but of functions. Now I come to the conclusion. So, what did this presentation cover? Was it about poetry, or programming, or physics? Not quite. It was about the CLJ tiles environment. The talk was first and foremost about showing a certain way of conveying ideas. I believe that it's a good thing to formulate ideas in a computer executable form. But that topic was already covered at Clojure 2020 by Sam Ritchie in his functional physics talk. That code is better than pen and paper is not the issue here. It is taken as a given. The point is rather that for the formulation, I did not live code as we know it. Instead, I was using the mouse. I solved graphical puzzles. In doing so, I was building up ideas step by step. I did not touch the keyboard. In this way, a lot of mental load was taken away from me. So I could fully concentrate on explaining the problem domain. The same holds for the viewers. Anyone can attempt to solve the puzzles just by opening a web browser. Indeed, the intention is that viewers follow along in real time. On the other hand, puzzles can be solved completely without guidance. For example, CLJ Tiles includes tutorials about the driven pendulum, fully covered with explanations and solutions. Any graduate student can start to solve them. As an outlook, let me spin this thought further. A physics tutor could base an entire lecture on those tutorials. In fact, a seasoned speaker certainly gives a much better talk than the best programmer. The aim is that the general method of explaining ideas with code gains wider adoption. The graphical user interface is there to lower the entry bar for both tutors and students to this new way. CLJ Tiles is open sourced under the GNU license. New puzzles can be added as the need arises. The person who adds them does not have to be a speaker. On the other hand, a subject specialist without coding skills can very well give advice or feedback to the puzzle creator. Of course, other domains outside of physics can be covered too. The rocket example I showed was an intro to web programming. Another field is data science. Those fields lend themselves even easier because coding is ingrained there. But I think the low entry bar is especially necessary in fields where coding is not the daily bread and butter. Maybe a reward system would help to engage people. Things like the spinning text shown at the beginning could help people playing with the puzzles. In any case, you need to remember one thing when it comes to graphical puzzles. You did not make an error, you just ran early.